Well, it gives me great pleasure to introduce the chair of the Material Science Department, Professor Naresh Thadhani, who I've known for 30 years probably at this point. I was just adding it up. The last decade of that has been as chair. He's stepping down here in July after a great term of service and going to return to his research, which is some very cool research, shock impact, gas gun work with sensing and modeling of that. If I know anything about Naresh, though, he's not going to talk anything about his own research. He's going to talk about the great stuff that's going on in the materials department. That's a very important part of the Institute for Materials and overall Georgia Tech. Thank you, Naresh.
Yeah. Thank you, Judd. So I was asked to give an overview of the materials-related research that's going on in the School of Material Science and Engineering. And actually, I will admit that I know just enough of what's going on in the school to really prove dangerous. Okay. So my colleagues who are here, if I go overboard in anything, please do correct me, or speak up as we go through. But what I want to do is start by first giving you a historical perspective of how we got to where we are today. Okay, and then I'll give you snapshots of research in areas that I've just topically grouped into different categories. Yeah, that will be the overall agenda for my talk. So just to give you an overall historical perspective, our roots are actually in the School of Textile Engineering. More than 100 years ago, the textile engineering program was actually the third program to start at Georgia Tech in 1897. And then, the Southeast U.S. is very known for the kaolin, mining, and the advent of that kaolin industry in 1924 led to the School of Ceramic Engineering, with the first Bachelor's of Science degrees initiated at that time. And then 1985 was when the School of Ceramic Engineering combined with the metallurgy program that was actually part of chemical engineering. Okay, it was a program within chemical engineering. So ceramics and metallurgy combined to form the School of Material Science and Engineering in 1985. So we are actually all, just, started in 1985. So relatively young school compared to like many other programs in the country. Textile engineering in its own way went through several reincarnations. And in 2003 was named as the Polymer, Textile, and Fiber Engineering Program, or commonly we used to call it as PTFE. Okay, and then 2010, the Polymer, Textile, Fiber Engineering merged with the Ceramics and Metallurgy program that were part of the Material Science and Engineering School to create what is today the largest and I believe one of the most diverse schools or programs in material science and engineering in the country. Most diverse in terms of the areas of research expertise that we represent. Okay, so to kind of give you a sense of the diversity of our research areas, I'd like to show this kind of a cartoon that is illustrative of our roots that are in the process structure property paradigm base for every material that we work with. That's what distinguishes materials disciplines, right, or other engineering disciplines. We look at how the process that is used to make the material influences the structure, structure in turn influences the properties, and properties are what dictate the performance. Okay, but what you'll see is that's how we are grounded. That's our, those are our roots, and then our tools are the different things that we do with the materials, right? The processing, the synthesis, the characterization, the modeling, the computations, et cetera, the environments that we subject different materials to, and the forms of materials. Notice that practically every form of material, is represented in our program, whether it's a metal, ceramics, polymer, composite, biomaterial, nanomaterial, textile, fibers, everything is represented in the material. And so are the applications. Okay, and you can see the applications that our faculty do research in, whether it's optoelectronic, photonic, bioenabled, magnetic materials, applications, packaging, energy systems, implants, orthopedic, name it, that area is represented. Okay, and finally, We all do this work for the purpose of addressing societal challenges. Okay, so the outer peel of this onion or this cabbage, whatever you want to refer to that as, is the addressing of the societal challenges. And literally every area of societal challenge is addressed by our faculty. Okay, so this is one way to look at it. The other way to look at it is how we have grouped our different research areas, and they essentially constitute, three basic areas: functional materials. Nag talked about all of the electronic, optical, materials, energy storage materials. Those sort of represent the area of functional materials. Then, of course, there are soft biomaterials. Okay, again, those soft biomaterials have overlap even in the functional materials. So these are not necessarily unique areas, but we kind of have grouped faculty in these different, interest areas, of course, with a lot of overlap amongst each other. And again, finally, the structural materials. So if you look at the challenges that each of these address, of course, structural materials relevant to infrastructure, transportation, security, soft biomaterials generally, health, sustainability, environment, although, significant activity in electronic materials as well coming up. And functional materials, essentially energy, communication, and intelligence type aspects. Okay. So in addition to that, you see there are two cross-cutting themes: characterization and measurements. Those, of course, span through all, materials forms, all applications, okay, and likewise computations and data analytics. Okay. So even though there are faculty that may be targeting computations perhaps in a certain application area or a material area, oftentimes these are cross, linked into multiple, programmatic areas also. So with that, let me now go through, again, as I said, snapshots of research that I've grouped in different categories, okay? And essentially, I'm going to start in more of an alphabetical manner, okay? So one of the areas is bio-enabled and bio-inspired materials. You mentioned this, so this is the first one I'm going to show. Okay, so again, this is an area that is quite active, not only in material science and engineering, but actually across Georgia Tech as well. Okay, and we have faculty, for example, Vladimir Sukruk. He's looking at, again, learning lessons from nature. How do different waterborne or airborne or ground crawling species have the ability to sense? Okay, and can we adapt those sensing abilities by creating structures at the nanoscale for different materials that we are working with? Okay, so these can be used for optical applications. These can be used for mechanical applications. These can be used for even thermal applications. For example, sensing the temperature changes with like a microkelvin degree temperature change. Okay. Very difficult, otherwise, but nature does it. Okay, so can we use those type of lessons to incorporate in that? Mohan Srinivasa Rao, he uses a lot of, again, you mentioned about the butterfly changing colors, the biophotonics, the bio-inspired mimicry of materials. Okay, so taking lessons from the 3D architecture that a butterfly wing has or other species have, can we implement those into materials? Can we synthesize materials to have those type of functionalities? Okay, again, a significant work going on in that area. John Reynolds works in a similar area, all the way from synthesizing polymers. Again, these are all organic materials that he's working on. So synthesizing polymers, processing these into, structures that have these electrochromic applications, for solid state and other electrochromic applications. By, again, using additional functionalities to trigger a certain response. Valeria Milam works on a different area, but using similar lessons from nature. So just as diseases spread by DNA, targeting particular cells, can we use similar lessons to actually do a colloidal assembly of nanoparticles? Okay, and have a pattern-based recognition that you can implement during the colloidal assembly of particles, and in turn grow the type of structures that you may want. Again, a very, very active area of research. In the area of characterization and in-situ measurements, There's a lot of work going on, both using facilities that are nationally available, like for example the synchrotron source, but also doing like in-situ X-ray diffraction or in-situ transmission electron microscopy. Okay, so for example, Faisal Alamgir does a lot of work in X-ray diffraction, looking at a lot of graphene-based structures, but again, designing cells that he can then take to the Brookhaven National Laboratory and do in-situ characterization, X-ray diffraction studies to monitor the phase changes, that are associated with different functionalities. Josh Catcher, he's looking at doing deformation studies or corrosion studies inside the transmission electron microscope. So imagine using actually a small corrosion cell inside your transmission electron microscope and monitoring. You see the pictures at the bottom here, where there is a corrosion area that is triggering, and you're monitoring in real time how that growth of the corroded region is expanding. Or if you're doing stress corrosion cracking or indentation, how is the deformation as well as the fracture path evolving, then you can observe that in real time. Matt McDowell does a similar thing where he's actually looking at electrochemistry that is relevant to battery applications, okay, and monitoring the phase changes as you pass a current and as the electrochemistry is taking place. What are those phase changes that are happening in real time? And doing those type of studies inside the transmission electron microscope. Okay, again, very, very powerful and useful techniques. Amit Garmastani, he's monitoring texture, looking at, again, phase transformations as a function of temperature, doing a variety of X-ray diffraction type of analysis. Again, in real time, monitoring those type of phase changes to kind of get the idea of what is responsible as the mechanism of whether a material is undergoing changes due to stress application or thermal changes that are triggering those type of processes. Because those are the methodologies that you can use then to create or design materials for specific applications. Computations and data analytics is, again, a cross-cutting theme, with Professor Dave McDowell looking all the way from the atomic scale to the end-use scale, or essentially the entire device being subjected to, the environmental conditions or the conditions that are imposed by the environment, all the way. So essentially linking what's happening at the molecular scale, at the nanoscale, and bridging those effects to get an overall effect of material response under extreme environments. Seung Jang is doing a lot of molecular dynamics type of studies, okay, focusing again in the area of biopolymers as well as energy storage or battery applications or catalysis applications or looking at membranes. So how do changes take place in materials, as a function of different chemical, different chemistries? One of the fascinating examples that I remember from his work, he was looking at a study sponsored by Bosch and Lomb on contact lenses. And of course, everybody wants different colors of contact lenses. So Bosch and Lomb was looking at, how will different molecular additions, change the dryness of the lens material. Okay. And rather than actually going through and making 100 of those different types and testing those, Seung Jang did a study or the computer did like the what if type of scenario changes, calculations, and came up with the responses of how the different dopants are going to affect the dryness or other mechanical properties of that material. So again, a very, very powerful use of computational material science. Carl Jacob, again, is looking more at the mechanics associated with polymeric materials, both from the perspective of the synthesis part, the processing of polymers, as well as the performance, or as you subject materials to certain loading conditions. Okay, doing all the way from, again, molecular type studies to continuum type of studies. Mo Lee, again, very much focused on the molecular level understanding of what happens to mostly metals, okay, as they melt. how do you understand melting? Melting may be thought about as a very simple thing, but how do you model the phenomena of melting? Or how do you model the phenomena of localized deformation that may take place in a material as it is subjected to mechanical loading conditions? Okay, so coming up with advances in these computational approaches to give us a very good understanding of these physical or mechanical changes as they take place in material. Rampi Ramprasad is our data analytics, machine learning person. Again, doing some very creative work, blending theoretical informatics along with machine learning and data analytics to come up with, all the way from discovering new polymeric materials, okay, for a variety of applications, or going all the way from the applications perspective and coming up with designs or formulations of what should those materials be that should give you those responses. Okay. He's just started a company that is called Matmerize that actually does very interesting, this type of discovery work where the entire platform of Computations is based on a cloud-based system that allows companies to, even put in their own data and make predictions. In the area of electronic materials, properties, and packaging, again, a very active area that we have several faculty working on. Natalie Stinglin, she's working in the area of organic functional materials. Many of the things you talked about, Nag, in terms of the DBRs, the optical devices, but from the perspective of organic components. Okay, even using these for bio-related applications. Lauren Garten, you're going to hear from her later, I think today or tomorrow, I forget. She's interested in understanding and synthesizing novel, forms of multiferroic, ferroelectric materials, dielectric materials. C.P. Wong did a tremendous amount of work initially in packaging, electronic packaging, but is now extending his understanding, his expertise, going beyond packaging and interconnects to wearable and printable devices, as well as energy harvesting type of application. Swami Madhavan is our director of the Packaging Research Institute, primarily computational person, but is doing a lot of work, in designing various types of, electronic systems, concentrating on packaging and beyond. Another area related to that, electronic devices, synthesis and fabrication. Mark Losego is an expert in vapor phase deposition techniques for both organic as well as inorganic materials, as well as the combination of organic on inorganic, or vice versa, the inorganic on organic. I think I said it correctly, but you understand what I mean. Again, doing very impressive works, again, for a variety of applications. Juan Pablo, who started just several years ago, again, doing very impressive work on perovskite type structures for solar cell applications. Rosario Gerhardt looks at process structure property evolution using her impedance spectroscopy technique for a variety of applications that are not just relevant to electronic applications, but also in the fabrication of complex composite type materials as well. Eric Vogel, you know a lot about him. He's looking at all the way from synthesis of materials, taking them to devices, to applications of devices, and specializing in 2D materials, doing some very impressive work there. And then Wensheng Kai is our expert in optical materials, looking at nanophotonics, optoelectronics, plasmonic materials, meta materials. That's again his basic expertise. Did I hear the bell ring? Or we are okay, right? Okay. All right. So again, doing some very impressive work in the optical area for optical applications. Energy storage and harvesting, again, a very impressive area, not only amongst the people that are shown on this slide, but some of the people I've already talked about. Melin Liu is our expert in fuel cells. as well as battery applications, looking at not only forms of materials, but understanding the physical of how the different electronic storage devices or harvesting devices are operating. Similarly, Gleb Yushin, you're going to hear from him in a little while. He's again working on different lithium-based battery materials for, again, a variety of applications. And the picture that you're seeing with Gleb standing there is part of his publicity related to his own company, Sila Nanotechnologies, that's today valued at more than $3 billion. Again, a really success story as far as that is concerned. Zichin Len is working on, patterning or using polymers as templates for creating a variety of nanocrystalline structures. It's amazing, like any type of nanocrystalline material you want is like a factory, he can make it, using his polymer as a template, and that it's also impressive with the type of names they come out with, the nanocombs and the nano brushes and all kinds of, core shell structures and those type of features, including quantum dots. There's an amazing spectrum of quantum dots that he's working on, both for optical applications as well as some of the work that I have collaborated with him, where we're actually using these quantum dots as sensors, as pressure sensors. But that's another game there. Satish Kumar, he's our expert in making fibers, and not just straightforward carbon fibers, but actually composite fibers, where each fiber itself is a composite. So for example, the picture of the cross-section that you're looking at, it can be a hollow fiber. What you're seeing are like holes in between, or it can be where those holes are infiltrated with a different material. So this individual fiber is a combination of PAN, the polyacrylonitrile, combined with carbon that contains a dispersion of carbon nanotubes. So not only does this give you the high strength, the strength increases almost like about threefold, but in addition, it also allows you to generate additional functionality. For example, electrical conductivity. So these are like really high electrically conducting fibers as well. Health and human welfare, in that area, we have people like Paul Russo, who's working on therapeutic drug delivery. Like, again, learning lessons to some extent from how diabetes spreads, but then countering that response to create capsules, or these cells or these containers that could contain the drug that then would be dissipated into localized areas rather than spreading all over the place. He's also looking at polymers that can be structured through ultrasonics. That you can create particular structures using ultrasonic effects. Blair Bretman is our polymer processing person, and she's doing a variety of processing, using a variety of processing approaches, including 3D printing, for again, a variety of applications, including pharmaceuticals. So there's a pharmaceutical component that she's also working on. Dong Chin is working on nanocrystals, generating and understanding what happens at the surfaces of nanocrystals that are relevant not only for catalytic effects, but also can be used as biocompatible nanoplatforms for sensing application. And Sundaresan Jayaraman, he's our textile engineer who initially designed the smart shirt, or a shirt with a motherboard in it. So it has the ability to do sensing as well as responding under given stimuli. But over the years has now been actually also working on textiles that are ideal materials for even like COVID masks, for masks that we are using today for COVID related protection. And extending this to some of the new advances in textile technology, where there is a machine vision controlled stitching process. So the stitching of garments, if you think about a pair of jeans, the legs part, you have a vision control process that brings the different parts of the garment together to allow automated stitching. So essentially what is referred to as like the seamsterless stitching. So really advancing the manufacturing operations that are related to, textiles, not for the purpose of just simple textiles, but multifunctional textiles or smart textiles that may have elements or fibers, for example, conducting fibers that would have the ability to sense and respond, or in whatever application that may be needed. In the area of infrastructure and transportation, again, we have experts that are working all the way from metals to polymers to composite materials. Misha Schaffner is working in the area of oxalic materials and tensegrity structures. And these are not necessarily like large-scale structures, the tensegrity structure that you see at the Mercedes-Benz Stadium, but in the context of molecular structure. So how can you create these tensegrity structures or the oxalic structures at the molecular level and therefore control the performance of materials? Dongyang Yao, he's working in the area of polymer processing, composite materials, the rheological studies, doing both processing as well as computational finite element type of studies. Yujing Wang is working on recycling of textiles and other composite materials, or those that are otherwise difficult to recycle. Marilyn Rialf is working again on the mechanics of fibers for textile-related applications. Chris Molstein is doing some very interesting work in the area of mechanical testing, all the way from very small nanoscale structures to large bulk structures. One of his, again, impressive things is to do mechanical property measurements of thin foils. Like ultra thin foils, if you hold it in your hand, the foil is so thin that it will just collapse into the structure of your palm of your hand. You can barely hold it. So how do you do a mechanical test of such a thin structure that you can't even hold? Okay. So he's doing some very impressive work in that area. And Preet Singh is our expert in corrosion testing, corrosion for some of the nastiest environments that are related to the paper industry as well as the oil industry. The environments that the metals face when they're subjected to these conditions are really, really nasty, and it's a real challenge to generate the fundamental understanding to see what's going on under these applications. In the area of materials in extreme environments and manufacturing, Robert Spire is working on making ceramics using a feedback loop control process for pressureless sintering of ceramics. Ceramics, for those who may know about it, it's very difficult to create 100% dense structures. And imagine now creating 100% dense structures in conformable shapes, okay, in any type of shape that you would want, okay. Using high pressure, it becomes very difficult, okay. So what he has been using is a pressureless feedback control sintering process to allow you to fabricate net shapes of ceramics. And some of the forms that are shown here are what are very impressive for use in like body armor type applications, so protection for soldiers and law enforcement officers. Aaron Stebner is our manufacturing and AI expert, particularly implementing artificial intelligence in manufacturing operations. And you can see, this is like showing tomorrow's factory. Thin film production can be automated very easily or relatively easily. Trying to automate large, metallurgical structures as you're going through fabrication of those is a major challenge. Okay. And Aaron Stebner is one of our lead faculty who's been working on this, of how, as the process is evolving, can you monitor the structure and properties in real time to give you a understanding that you can implement as a feedback loop in altering that process. And Judd, I have to talk about my work too, right? 10 seconds, right? Okay. So I work in the area of high strain rate deformation. So essentially understanding what happens to materials in terms of the mechanical changes, the physical changes, the chemical changes that happen in materials when they are impacted under very high velocity impact conditions. So with the time of pressure generation is of the order of nanoseconds to microseconds. Okay? And the understanding needed there, the devices that are needed to monitor and understand are really mind-boggling, and that's what we are working on. We have the ability to do these impact experiments and a suite of diagnostic capabilities as well as computational approaches to understand what's happening in the material. Okay. So that was what is in material science and engineering, and I would not do justice by ending there because as Eric mentioned earlier, materials research is not just being performed in the School of Material Science and Engineering. We actually have 40 tenure track faculty in material science and engineering. But across Georgia Tech, there are more than 200 faculty that are doing like literally full-time materials related work. Okay, and a lot of those faculty are in biology, physics, chemistry, biochemistry, aerospace engineering, civil engineering, electrical engineering, chemical engineering, mechanical engineering, literally every unit on campus. And of course, we have a wide range of interdisciplinary research institutes as well, not just the Institute for Materials, but the Renewable Bioproducts Institute, the Georgia Tech Manufacturing Institute, the Institute for Electronics and Nanotechnology, I may have missed some, the Georgia Tech Research Institute, okay. So there's a lot of work going on in materials-related area. Maybe the last thing I will say is that maybe Georgia Tech is really the Walmart of material science and engineering, not to say in any negative manner, but really we have a lot of expertise in materials. Okay. Before I end, I do want to make a pitch for, the research is not just at the high level, okay? Not just at the level of faculty or postdocs and research scientists or graduate students. It also trickles down all the way to the undergraduate level, okay? And this is our concept of a materials innovation and learning laboratory. This is our open access make and measure space, which is operated, led, managed by a C-suite of undergraduate students. Okay. We have a CEO, a CTO, a chief communications officer, a chief safety officer. Please don't ask me their salary because you'll be disappointed. Okay. But these are an amazing group of people that are looking over about $800,000 worth of equipment that is available to undergraduate students right away from the day they step foot on campus. Okay. And it's an amazing faculty, and this is what you get when research really trickles down at every level and integrates every aspect of our fabric. So with that, I'm going to stop, and I thank you all for your attention. Happy to answer any questions.
Thank you, Professor Thadhani. Any questions? Well, I'll ask one. It won't be mechanics of properties, which you taught me so long ago. So now that you're stepping down, where do you hope to take your research? We'll let you answer that one. Where do you want to take your research now that you'll actually have time to do that and not have to choose donors and other sorts of things? All right, what are you looking forward to the most now that you'll have time? Well,
I've actually never stopped my research, so maybe the pace will increase. But I think some of the areas we're looking at is real-time monitoring of what happens in materials as they're subjected to these high-velocity impact conditions. So imagine your car, okay, your bumper, okay, you had a rough accident. Is there a way to monitor, by placing a sensor? And no, I'm not talking about like a patchwork of circuitry, but maybe the material itself also has sensing ability as a coating or something that is integrated with the material that gives you every indication of the stress that was generated, the time over which was the stress was present, okay, and perhaps even some healing options. where there is a release or pressure release of some manner that provides protection or healing. Okay. I think that would be the direction I would go. To kind of put it in a very simple manner, but it's not just related to mechanical changes, it is also associated with chemical changes and physical changes.
Multifunctionality, we see that in so many different materials being advanced. So check, see if we've got any questions. I'll take one more. What are you most proud of over your tenure here as chair, and how do you expect that to continue? I mean, when I came in here in '89, just a few years after the thing was formed, we weren't ranked, and now we've been ranked in the top 10 for a decade now or something.
I think I'm proud of the people we have, all the way from the faculty, staff, and the students, and our ability to work with each other. Go across, hallways, across buildings, talk to people. I mean, as I said, I worked with, Zichin Lin, and prior to him, Chris Summers, in a completely different area, of electronic materials, where we are using these quantum dots, or actually your DBRs. You talked about the DBRs. We are working on optical microcavities as well as sensors.